All right, in this example, there's a skateboarder that has a mass of 40 kilograms, and the skateboarder has a speed of 1.5 meters per second at the top of the slope, and the height of the slope is 3 meters high and 16 meters long. At the bottom of the slope, the skateboarder's speed is 6.5 meters per second. And the question is asking, are there any non-conservative forces present? And so in order to test this, we basically need to see if energy is conserved. If energy is conserved, then there are no non-conservative forces. But if there is a change in the energy between the top and the bottom, then there must be some non-conservative forces present. So I can start by determining the energy of the skateboarder at the top, which would be our initial position. And the skateboarder can have kinetic energy and may also have gravitational potential energy. And since I know how fast the skateboarder is going, I know their mass, and I know the vertical position, I can calculate that. And we are going to assume that the lowest position here would be our 0 position, and so our initial height, our initial vertical position is just whatever the height of this is. So this would be 1/2 the mass, which is 40 kilograms, times the initial speed squared, and then plus the gravitational potential energy, which is mass times gravity, times the vertical height of 3 meters. So when I plug those values in, I end up getting 1,221 joules. All right, well, the next would be to determine what the energy is at the bottom. And so we would want to find the final energy of our system, which would be the kinetic energy final plus the potential energy final. But our final position is just 0 because we're back on the ground. So we don't have any potential energy. All we have is kinetic. So this would be 1/2 the mass, which is 40 kilograms, times the speed at the bottom, which is 6.5 meters per second squared. And when I plug in those values, I get 845 joules. So what we find is that the energy initial is not equal to the energy final, which means energy is not conserved, and there must be some non-conservative force present that is doing work, which is taking energy out of the system. So the next part of the question says, if there are any non-conservative forces, so if so, what is the magnitude of the non-conservative force? And we're going to assume the force is constant and parallel or anti-parallel to the displacement going down the incline. And we need to ask ourselves, is this force actually helping the motion or hindering the motion? Since we're losing energy, then that means that the force that's present is actually hindering the motion, which means it would be going opposite the direction of the motion down the incline. So we'll keep in mind that we know the energy initial and we know the energy final. So let's write down those values. So we know the energy initial at the top is 1,221 joules, and we know the energy at the bottom was 845 joules. So we want to determine the force that's present, and so in my picture, I'm going to go ahead and draw the force being opposite the motion. So it's likely friction, right there, but it could be any force. So we'll just call it, put in parentheses here, friction, but it really could be any force, but friction is one option. So we know that because the energy is not equal, it's not constant, that the net work done by non-conservative forces has to equal the change in energy, which is just the final energy minus the initial energy. So we know we can calculate what this change in energy is. The final energy is 845 the initial energy is, the initial mechanical energy is 1,221. So the total amount of change in energy is negative 376, right? We've lost mechanical energy in our system. And this is because of this non-conservative force. So the force is doing work, and they've told us that it's either parallel or anti-parallel to the motion and that it's constant. So the work done here is the work done by some force that is occurring through some displacement, and then there could be an angle between that force, and that has to equal this change in energy of our system. So because the energy is decreasing and because they told us the force was parallel to, or anti-parallel to the motion, we know that the angle here is 180 degrees because it's losing energy and the force must be opposite the motion. So we're trying to find this force. The displacement down the incline where the force acts is 16 meters, and then cosine of 180 is going to just be a -1. So we can solve for the force. So the force is just negative 376 divided by 16, and then cosine of 180 is -1. So we get that the force that's being applied is 23.5 newtons acting opposite the motion. This is the magnitude of the force. So this is one example where we've used the work energy theorem instead of applying Newton's laws of motion to calculate the force. So of course the other approach would be assuming that the force is constant. We know the distance covered, we know the change in the speed, so we could have used kinematic equations to find the acceleration, and then based on the acceleration we could solve for the force. So remember that work energy is just another approach to looking at problems that are similar to things we've seen before when we're talking about motion.